Hi everyone, welcome to this data annotation course. I'm your instructor, and today we're diving into the first part of the material. Hope you're ready, let's get started.
In Chapter 7 of the Artificial Intelligence Technology Application Core Course Series textbooks, we'll focus on 3D point cloud annotation. The topics include an introduction to 3D point cloud labeling, a 3D point cloud annotation tool, a 3D point cloud labeling project, a chapter summary, as well as homework and exercises. A point cloud is like a cloud made up of points. Usually, it comes from LiDAR, and it can also be sourced from millimeter wave radar. It's a collection of 3D points generated by these sensors. Point clouds can be categorized into black and white and color types. Point cloud data, obtained by 3D scanning equipment like LiDAR, contains information such as XYZ position, RGB color, and intensity of several points in space. It's a multi-dimensional complex data collection. First, let's talk about the binocular vision sensor. It's similar to human eyes and works based on the principle of parallax. It acquires the 3D geometric information of objects from multiple images. A binocular stereo vision system can get two digital images of the measured object from different angles simultaneously using dual cameras or at different times using a single camera. Then, it restores the 3D geometric information of the object according to the parallax principle. In the picture, the left and right cameras together form a binocular vision sensor. Next is the LiDAR. LiDAR, which stands for Light Detection and Ranging, is a radar system. It emits laser beams to detect characteristics like the position and speed of a target. Its working principle is to send a detection signal, that is, a laser beam, to the target. Then, it compares the received signal, the target echo, reflected from the target with the transmitted signal. After proper processing, information such as the target's distance, azimuth, height, speed, attitude, and even shape can be obtained. Now, the Depth Somatosensory Device Kinect. It's similar to a 3D camera, and has functions like real-time motion tracking, image recognition, voice recording, and identification. The left and right lenses are an infrared emitter and a CMOS infrared camera, respectively, which identify a depth field. The color depth of each pixel indicates the distance of the point from the camera. Points closer to the camera have brighter colors, while those farther away have darker colors. One application of 3D point clouds is multi-view 3D reconstruction. This method restores the 3D model of a scene by using multiple images from different perspectives of that scene. Multi-view 3D reconstruction of natural scenes is a fundamental problem in computer vision and has a wide range of applications. The figure shows a schematic diagram of this process. Another application is 3D simultaneous localization and mapping, or SLAM. It mainly solves the problems of positioning, navigation, and map construction when mobile robots operate in an unknown environment. The figure shows a schematic diagram of 3D simultaneous localization and map construction. 3D object detection is also an important application. Compared to 2D images, 3D point cloud data can better represent the surface and some depth information of objects. With many sources of 3D point cloud data, research on it has grown rapidly, promoting the use of deep learning for 3D point cloud target detection. The figure is a schematic diagram of 3D target detection. 3D semantic segmentation is widely used in fields like medicine, autonomous driving, robotics, and augmented reality. The figure shows a schematic diagram of 3D semantic segmentation. 3D point clouds are often stored in formats like PCD, PLI, and STL, with encoding methods of ASCII code and binary. Although formats may vary by device, they can all be post-processed into the standard PCL file format. PCD. Currently, 3 PCD formats can be recognized: ASCII, binary, and binary compression. The table lists 3D point cloud storage formats methods and data types code and The Sydney Urban Object Dataset contains various common urban road objects scanned by Velodyne HDL-64 ELIDAR in the Central Business District of Sydney, Australia. It has 631 individual scanned objects, including vehicles, pedestrians, advertising signs, and trees. The figure shows a sample of this dataset. The Large-Scale Point Cloud Classification Benchmark Dataset provides a large labeled 3D point cloud dataset of natural scenes, with over 4 billion points. It covers a wide range of urban scenes, such as streets, railway tracks, squares, villages, football stadiums, and castles. The figure shows a sample of this dataset. The RGB-D Object Dataset is a large dataset of 300 common household objects. It was recorded using a Kinect-style 3D camera, which records synchronized and aligned 640 x 480 RGB and depth images at 30 Hz. The figure shows a sample of this dataset. The New York University Depth Dataset includes the NYU Depth V1 and V2 datasets. The data consists of video sequences from various indoor scenes, composed of RGB and depth from a Microsoft Kinect camera. The figure shows a sample of this dataset. The KITTI Standard Dataset uses a large number of urban environment point cloud datasets collected by KITT's unmanned vehicle platform. This dataset has radar, image, GPS, INS data, as well as artificially marked segmentation and tracking results. It can be used to objectively evaluate the effect and performance of large-scale 3D modeling and fine classification. The figure shows a sample of this dataset.